9.10 Lesson 6, Taylor and Maclaurin Series. Our objectives for today's lesson are: you'll know the Taylor series centered at 0 for a function of the form f of x is equal to 1 plus x to the k, called a binomial series. And once we know that, you'll be able to use the binomial series to find Taylor series centered at 0. We call those Maclaurin series for functions of the form f of x is equal to 1 plus x to the k. Vocabulary: binomial series. These are the guidelines for finding a Taylor series from an earlier lesson. So you are going to use the definition of Taylor series. So that's step 1. Differentiate f of x several times and evaluate each derivative at c. The reason you need to do that is because how do you form a Taylor series? You use this definition. So you need to know the value of the function at c and the value of its derivatives evaluated at c, so you can form these coefficients of your Taylor series. So you form a Taylor series from the function, and then you write a rule for the nth term, and then you use the ratio test to determine the interval of convergence, and then you have to use theorem 9.23 to determine whether the series converges to the function from which it was derived. We will not be going over that as a part of today's lesson, and we will also not be looking at the ratio test. But in fact, what we are going to look at today is step 1, and it is true that both of these will happen. We're just not going to cover that in our lesson today. So there is going to be an interval of convergence, which you can find by using the ratio test, and you can also use theorem 9.23 to show that the Taylor series will in fact converge to the function from which we will derive it. So we're taking a look at objective 1 here. You'll know that the Taylor series centered at c is equal to 0 for a function of the form f of x is equal to 1 plus k, f of x is equal to 1 plus x to the k power is called a binomial series. So what we're going to do is we're going to go ahead and apply the definition of Taylor series, which I am circling in green. So what we must do is we must evaluate our function, which I underlined here, at the center, which will be 0. So what is f of 0? F of 0 will be 1 plus 0 to the k power. So that would be 1 to the k power, and that would just be 1. 1 raised to any power is 1. So using the definition of Taylor series, what we must do is we have to form the coefficients of our Taylor series. So we have to find derivatives of our function f, and we have to evaluate each of these derivatives at c, which for us will be 0. And of course, don't forget to divide by the appropriate factorial expression. It'll just be n factorial in general. So how do you find the derivatives of f of x is equal to 1 plus x to the k? Well, you're going to use the power rule because you're differentiating with respect to x. X is the variable that we're differentiating with respect to. And you see x here in the base of the power. So you use the power rule to differentiate. So all you do is you take the exponent, bring it to the front, and subtract 1 from the exponent. And that's how you get f prime. F prime is k times 1 plus x to the k minus 1. And if you evaluate f prime of x at c is equal to 0, so that you can write that in here in the definition of a Taylor series, then you're going to have f prime of 0. You would substitute 0 for x, so you get 1 to the k minus 1 power. 1 to any power is just 1. So you just have k times 1, and that's how we get k there. And what do you do with that k? You write that in the definition of a Taylor series. So you see that here. f prime of 0 is k, so I have k here, and of course I have k times x. F of 0 is 1, as you see here at the bottom, and I write that for f of 0. So that's why we're finding the derivatives and evaluating them at 0, because that's what we need to do to form our Taylor series from this function. So what are we going to do next? We have f double prime of x, and all you do is take the derivative of the first derivative. So use the power rule again, bring the exponent to the front, and subtract 1 from the exponent. And you need to evaluate the second derivative at 0 and divide by 2 factorial to form this coefficient of the second degree term from the Taylor series. So now that we have the second derivative, we'll evaluate it at 0, substitute 0 where you see x. Well, there's only one place where you see x, and that's right here. So when you substitute 0 for x, you get 1 to the k minus 2 power, which will just be 1. So you just have k times k minus 1, and that's why I have that here. So I replace f double prime of 0 with k times k minus 1 and divide by 2 factorial. And I have, of course, x squared. So I just keep going. I need to find the third derivative now. Again, how do you find the third derivative? You take the derivative of the second derivative. So here's our second derivative. To take the derivative of that, you're just going to bring the k minus 2 out front. So you have k times k minus 1 times k minus 2. And then, of course, you will subtract 1 from the exponent. So that's f triple prime of x. So you have f triple prime of 0. How do you do that? Once again, you need to evaluate the third derivative at x is equal to 0. There's only one place where you see x, so replace that with 0. So you get 1 to the k minus 3 power, which is just 1. So you just get k times k minus 1 times k minus 2. So you're going to replace the third derivative of f at 0 with k times k minus 1 times k minus 2. Divide that by 3 factorial, and of course you have x cubed. So that's what you need to do to form the coefficients of the Taylor series. So now you're going to go ahead and take the derivative of the third derivative to get the fourth derivative. Again, you use the power rule. This is what you have. Evaluate that at x is equal to 0. This term becomes 1, so the derivative would be just what you have there. And if you, and then of course you need to write that in the definition of Taylor series. If you continue with this, this is what you will observe. So if you continue here, each time you're taking the derivative, you might see a pattern. For example, if you're taking the fourth derivative, the very last term, or the very last factor here would be 1 plus x to the k minus 4. And for the third derivative, the very last factor here is 1 plus x to the k minus 3. And for the second derivative, the very last factor is 1 plus x to the k minus 2. So for the nth derivative, the very last factor will be 1 plus x to the k minus n. And what else do you notice in terms of a pattern? For the third derivative, you have k times k minus 1 times k minus 2. For the fourth derivative, you have k times k minus 1 times k minus 2 times k minus 3. And you can see that you have k minus 2 here, and of course 2 is less than 3. This is the third derivative. Here you have k minus 3, and of course 3 is 1 less than 4 for the fourth derivative. So in general, for the nth derivative, you'll have k minus a quantity that's 1 less than n, or you'll have k minus n minus 1. That's what you'll have. And again, where do we see that pattern? For the third derivative, we have k minus 2. 2 is 1 less than 3. For the fourth derivative, we have k minus 3 as a factor there, and 3 is 1 less than 4. So for the nth derivative, we'll have k minus n minus 1. But you can distribute the negative sign, and that would give you k minus n plus 1. So that's where that comes from. And if you evaluate the nth derivative at 0, this part, or this factor will become 1, and you'll just have all of that. And that's where that comes from. So you just take that and substitute for the coefficient of the nth term from the definition of Taylor series to get what we have here. So when you do that, you derive what we call the binomial series from the function f of x is equal to 1 plus x to the k power. And that's what you have here at the very bottom of our power series for elementary functions. And what is the interval of convergence? You could use the ratio test to verify this. It is from -1 to +1. The convergence at -1 and +1 will depend on the value of k. So we're not really going to focus on that. We're going to focus more on just being able to represent our binomial series or our functions of this form with binomial series. But in fact, this is the interval of convergence. And does this power series converge to the function from which it was derived? To answer that question, you would have to use theorem 9.23, but the answer is yes. But we won't go over that. So you will know that the Taylor series centered at 0 for a function of the form f of x is equal to 1 plus x to the k is called a binomial series, and we just looked at that. Now we will look at an example. You'll be able to use the binomial series that we just saw to find a Taylor series centered at 0 called a Maclaurin series for functions of the form 1 plus x to the k power. So basically we'll apply what we just saw for different values of the exponent k. So here we have an example of a function that fits this form, 1 plus x to the k power. We have f of x is equal to the square root of 1 plus x. But of course, we know that we can rewrite the square root as raising the radicand, 1 plus x, to the 1/2 power. So we have a function that fits the form 1 plus x to the power k. And in our example, k would be equal to 1/2. So if we want to form a Taylor series for this function, we're going to go ahead and use what we just saw. This is what we call the binomial series. And how do you form the coefficients of the binomial series? You have to look at the value of k, which for our example will be 1/2, and you need to write that wherever you see k in the binomial series. So we're going to do that. So first we begin with 1, so we have 1, and then we write k times x. K is 1/2, so we have 1/2 x, and then we write k times k minus 1, so I have 1/2 times 1/2 minus 1, which we can write as 1/2 minus 2 over 2 is 1, over 2 factorial times x squared, and then we have k, which is 1/2, times k minus 1, which is 1/2 minus 1. We can write 1 as 2 over 2, times k minus 2, which would be 1/2 minus 4 over 2 is 2, over 3 factorial times x cubed. And the pattern continues. What would be the fourth term? It would be k times k minus 1 times k minus 2 times k minus 3 over 4 factorial times x to the 4th. So that's what we have from the binomial series. So the rest of the process is to simplify what we have here and then try to represent our binomial series using sigma notation. So for simplification, there's really nothing you need to do for the first two terms. They're about as simple as it's going to get. There is something you can do for the third term. You can subtract 1/2 minus 1. 1 half minus 1, I already have a common denominator of 2 here. 1 half minus 2 over 2 would be negative 1 half. So that's what I'm doing for this line. I'm simplifying a little bit at a time. So I can go ahead and simplify 1 half minus 1, which would be negative 1 half, and 1 half minus 2, which would be negative 3 halves. And for the next term, the coefficient would simplify as follows. 1 half minus 1, which is negative 1 half, 1 half minus 2, which is negative 3 halves, 1 half minus 3, which is negative 5 halves. So that's all I'm doing for simplification to go to this line. How do we go to the line after that? Again, there's really nothing to do with the first two terms, so we just leave that alone. So what about the third term, the second degree term? How can we simplify that? Well, you can multiply 1 half times negative 1 half. So you get a negative product. And basically you get negative 1 over 2 to the second power. But then you're dividing that by 2 factorial. How do you divide negative 1 over 2 to the second by 2 factorial? You divide by 2 factorial by multiplying by the reciprocal of 2 factorial, which is 1 over 2 factorial. So that's how you get negative 1 over 2 to the second times 2 factorial. And of course you have the x squared. For the third degree term, when you simplify it, again when you multiply, you have a negative times a negative, which will give you a positive term. And then look at what happens here. You have 2 times 2 times 2, which is 2 to the third. And you have 2 to the third divided by 3 factorial. And then how do you divide by 3 factorial? You multiply by the reciprocal of it. So that's how you get the plus 2 to the third times 3 factorial in the denominator. What about the numerator? Well, the numerator is coming from the 1 times the 3, which I write as 1 times 3. And the reason I write 1 times 3 is, you'll see why in a little bit. So that's how we do the simplification to get this term. Now let's look at how we can simplify what we have here to get this. First of all, you'll see that you have a product of 3 negative factors. So you're going to have a negative term. Second, you have, of course, the x to the fourth. Second, you're going to look at 2 times 2 times 2 times 2, which is 2 to the fourth. But that's coming from the denominator of the factors that we have in the numerator. So you have the negative factor, and you have 2 to the fourth. And then you have 1 times 3 times 5. And all of that is divided by 4 factorial. But how do you divide? You multiply by the reciprocal. So you multiply by 1 over 4 factorial. So when you do that, you get 2 to the fourth times 4 factorial. That's what I have here. You get a negative term because you have a product of 3 negative factors. And then in the numerator, you have a pattern. You have 1 times 3 times 5. And then you have x to the fourth. So that's what we've been able to do. How do you write the sigma notation? Sometimes it's easier just to exclude the first couple of terms from the sigma notation. And that's what we're going to do here. We're going to exclude the first couple of terms, and we'll start representing the rest of the terms from our series using sigma notation. So we start with x to the second. So it's easy to just make the lower limit of summation 2, so you can just have x to the n to get x to the second for the first term. And then you need to make that a negative term, so you have negative 1 to the n plus 1 power, because negative 1 to the second will give a positive 1, but we want this term to be negative, so we need to make negative 1 to the n plus 1 power. So I've explained this so far. The next easiest thing to explain would be what I have here. That's pretty easy to see because you can see that you have a pattern. You have 2 to the n power times n factorial. So if n is 3, you have 2 to the third times 3 factorial in the denominator. If n is 4, you have 2 to the fourth times 4 factorial in the denominator. So generally, you'll have 2 to the n times n factorial. What we want to focus on is what I have here, which is supposed to represent the numerators. And maybe it would be easier for you to understand this if I were to maybe write out one more term here so you can see the pattern more clearly. So to write out an extra term, I can go to my very first line here, and just using the definition, just using the binomial series, to write the coefficient of the fifth degree term, I'll have k times k minus 1 times k minus 2 times k minus 3 times k minus 4. And all of that will be over 5 factorial. And I'll have, of course, x to the fifth. Now, when you simplify that to see what we should have here for this line, you'll have 1/2 times 1/2 minus 1 will be negative 3/2. And 1/2 minus 4/2 will be negative 5/2. And 1/2 minus 6/2 will be that's the negative 5/2 that I already wrote. And then 1/2 minus 8/2 will be negative 7/2. So that's what we'll have, and that'll be 2. And then we'll have that divided by 5 factorial times x to the fifth. Let's do that again, just because I think there was something that I messed up on. So again, we're starting here, and this is what we should have, just using the binomial series. So when we simplify, what should we have for the next line, for the coefficient of the fifth degree term? This is what you should have. You should have 1/2. 1/2 minus 1 is negative 1/2. So that's what I was missing. I think I was missing something. And then you have 1/2 minus 4/2 is negative 3/2. And then you have 1/2 minus 6/2 is negative 5/2. And then you have 1/2 minus 8/2 is negative 7/2, all times x to the fifth over 5 factorial. So the main thing that I want you to see is how do we go from what we wrote here in green to what we should have here for the next line. So when you multiply these 4 factors, you'll see that because you have 4 negative factors, the product will be positive. And then you have 2 times 2 times 2 times 2 times 2, so that's 2 to the fifth power, divided by 5 factorial, so you have 2 to the, so again, the product will be positive, and you'll have, let's write it here, the product will be positive, and you'll have, in the denominator, you'll have 2 to the fifth times 5 factorial, and that would be, of course, to the x to the fifth power. And in the numerator, look at what you see here. This is what I wanted to show. You have 1 times 3 times 5 times 7. 1 times 3 times 5 times 7. And this is what we're focusing on. How do we represent that pattern that we have in the numerator when we try to describe the nth term in our sigma notation? You have to recognize that in each of these terms, you always start with 1 and you multiply by the next odd integer and then you multiply by 5. So you actually have to represent that pattern that you have. It's not just enough to write something for the last factor that you have in the numerator, because it's not just 7, it's not just 5, it's not just 3. Here it's 1 times 3, here it's 1 times 3 times 5, here it's 1 times 3 times 5 times 7. So you need to describe that pattern. So you write 1 times 3 times 5, and so on, and you need to basically say when you should stop. You should stop when you get to 2n minus 3. How do you know that it should be 2n minus 3? You can just look to see what the pattern is. So again, n here for this term will be 5, and 2 times 5 is 10, and 10 minus 3 is 7. So it holds for the last factor in the numerator of the 5th degree term. Does it hold for the last factor in the numerator of the 4th degree term? 2 times 4 is 8, 8 minus 3 is 5, so it holds. What about for the last factor in the numerator of the coefficient of the 3rd degree term? Well, I would have 2 times 3, which is 6, and 6 minus 3 is 3. And what about for the 2nd degree term? I start at 1, what do I end at? 2 times 2 is 4, 4 minus 3 is 1. I start at 1 and I end at 1, so I just have 1. So today we looked at the Taylor series centered at 0 for a function of the form f of x is equal to 1 plus x to the k. We call that a binomial series. And we use that to find binomial series. We were able to use the binomial series to find Taylor series centered at 0 for functions of this form. And we did an example where k was equal to 2.